One day, in one of my high school math classes, I was introduced to a sequence that I'm sure every mathematician has pondered at least once. The sequence goes 1, then 1 plus 2, then 1 plus 2 plus 3, and so on. The nth number of the sequence is the sum of the first n natural numbers. The purpose of the lesson was to learn sigma notation, how we can unambiguously express the sequence like this. But the teacher threw in a bonus, a clever proof that this sum is actually equal to n times n plus 1 divided by 2. This really fascinated me, not just because of its elegance and simplicity, but because it extends the domain of the sum. The original sum is discrete. It only makes sense to plug whole numbers into it. For instance, if we tried to plug in 1/2, we wouldn't even know what to do. But the new formula is continuous. It has no problem handling any number you throw at it. So, if you're like me, you'll wonder, what other sums can be extended this way? Well, there are endless sums you could try, maybe the sum of squares, or the sum of cubes, or maybe even the sum of powers of 2. And all these examples actually do have fairly simple solutions. But the topic of this video will be a deceptively simple sum that I think is underrepresented: the sum of reciprocals. The numbers generated by this sum are called the harmonic numbers, due to a connection between reciprocals and the harmonic overtones of a sound wave. Anyway, because of this name, I will denote the nth harmonic number by capital H of n. So now let's take a look at these harmonic numbers and graph them on the plane. H of 1 is 1, H of 2 is 1 plus a half, H of 3 is 1 plus a half plus a third, H of 4 is 1 plus a half plus a third plus a fourth, and so on. Again, the proper way to define them is with sigma notation. H of n is the sum of 1 over k, as k goes from 1 to n. Now, to reiterate, this video will be exploring the question of how we can extend these numbers to the reals. A more visual way to frame the question is to ask, what curve can we draw that connects all these points in a natural way? Obviously, it's trivial to just connect the dots with a pencil, but we're looking to find one solution that we can say is correct in some sense. Well, in absence of any obvious direction to go, we might as well toy around with the harmonic numbers a bit and see what we can discover. So as a starting point, let's take a look at H of 49. To calculate this, we'll need to add up 49 reciprocals, which will take a lot of time if we don't have a calculator. But we can do it, and we'll get that it's about 4.4792. So now let's say we want to find H of 50. We could go through the whole process again and add up all 50 reciprocals, but that would be a huge waste of time because we've already calculated the first 49. So we can just take our solution for the first 49 that we already have and add 1/50th to it. This shortcut generalizes to any value of n. When we write h of n as 1 plus a half plus a third all the way up to 1 over n, we can take all the terms except for the last. And those are just the sum of the first n minus 1 terms, which is the definition of h of n minus 1. So we can just substitute h of n minus 1 in, and now we've got a new formula. This is a recursive formula, meaning it tells us a value based on the previous value. Now I'm going to introduce two simple variations of this formula that I hope will make its use a bit more clear. First, on the right, we'll shift the index by 1, replacing all instances of n with n plus 1. This is the same formula, but now it's framed to make it clear that we're using it to find the next harmonic number. On the left, we can just rearrange the equation a bit to get this variation, which is framed to make it clear that we can find the previous value. To see this formula in action, let's pretend that we've somehow forgotten the actual summation definition of the harmonic numbers, but somehow we magically know what h of 5 is. We can use the forward recursive formula to find h of 6. Just plug in h of 5 and add 1/6. And then we can do it again to find h of 7. Just plug in what we just got for h of 6 and add 1/7. And we can repeat this as many times as we want, which lets us find all the whole numbers greater than 5. Likewise, we can use the backwards recursive formula to go in the opposite direction. Just plug in the value for h of 5 and subtract 1/5. And just like with the positive formula, we can repeat this all the way down. And now we've rediscovered all the harmonic numbers that we started with based on just this recursive formula and one starting point. But we can actually go one step further. If we plug h of 1 into the backwards formula and subtract 1 divided by 1, we can find that h of 0 is 0. So we've just added 1 point to the list of points that we know, which, I mean, isn't much, but it's progress, right? But why end there? Can we go even further and find h of negative numbers? Well, unfortunately, this doesn't really work out. If we try to find h of negative 1, we plug in h of 0, but then we have to subtract 1 divided by 0, which we all know you can't do. But there's no need to worry. The usefulness of the recursive formula does not end with 0. Its real magic is that it isn't restricted to whole numbers. Unlike our original discrete sum, there's nothing about it that doesn't work for fractions or any real numbers for that matter. It's just an addition and a division. This means that we can move our starting point off of the integer value that it started on, and all the other points have to follow. We can see that though we couldn't calculate h of negative 1, other non-integer negative values seem to work just fine, although things go a bit crazy on the negative side. Since we can deal with real numbers now, I'm going to change all the n's in our equations to x's because n's commonly represent integers and x's commonly represent real numbers. Anyway, the fact that we can use real numbers now means that if we somehow could figure out what h of 1/2 was, we could repeat the recursive formula forever and find all the values that are 1/2 more than an integer. And this would effectively double the amount of points that we know. But even more powerful than that, if we could somehow figure out an entire interval 1 unit long, we could apply the recursive formula to every point on that interval, and that would give us the next interval. Then we could do it again, giving us the interval after that, and we could go on forever, solving the entire function. This simplifies our goal a lot, because now we only need to find one interval, and we get the rest of the function for free. But before we get ahead of ourselves, I'd like to introduce one more variation of the recursive formula that we'll eventually need for our solution. Earlier, we were able to find the harmonic number 2 steps up by applying the formula twice. The first time, we used h of x plus 1 is h of x plus the reciprocal of x plus 1. And the second time, we'd say that h of x plus 2 is h of x plus 1 plus the reciprocal of x plus 2. But since our x plus 2 formula references the x plus 1 formula, we can plug our x plus 1 formula into it, and the resulting formula gives us h of x plus 2 in terms of h of x. And we can do this a second time. We can write h of x plus 3 in terms of h of x plus 2, and then plug in this h of x plus 2 formula. And now we have h of x plus 3 in terms of h of x. And of course, there's nothing stopping us from doing it again with h of x plus 4. I think it should be pretty clear what the pattern is. To find h of x plus 4, we're starting with h of x and adding up the reciprocals of x plus all the natural numbers from 1 to 4. So we can condense this by using sigma notation, and we'll just replace the 4's with n's to generalize the formula. I'll call this the super recursive formula, because it's more powerful than just our recursive formula, which only steps 1 at a time. Alright, with that out of the way, let's get back to our main task. Remember, we discovered that we only need to solve one interval of the function to get the entire thing. So let's just travel up our graph and see if we can find an interval that we can solve. Note that as we travel up the graph, the slope gets smaller and smaller. And this should pretty much make sense because the bigger the number we put in, the smaller the reciprocal we're putting in, so we're adding less each time. In fact, it flattens out so much that by the time we get to h of 100, we've barely gone up more than 5 units, and we can hardly even tell that it's increasing at all. But compared to the infinite amount of numbers that exist, 100 is pretty much nothing, so let's keep going. And now I've skipped ahead and arrived at a huge value, which we'll call capital N. Up here, the points are so flat that we can pretty much say they're all the same height. That is, h of capital N plus 1 and h of capital N plus 2, and h of capital N plus 3, and so on, are all roughly equal to each other. We can condense this and just say that h of capital N plus lowercase n is pretty much equal to h of capital N, where lowercase n represents a reasonably small whole number. The bigger the capital N you choose, the better the approximation. For instance, if capital N is 1,000, you only have about 1/1000th of difference between each point, which gives you 2 decimal places of accuracy. Now if we chose 1,000,000 instead, we could get 5 decimal points of accuracy. And since there's no limit to how big n can be, there's no limit to how close this approximation can get. Now, I'll ask, what should our continuous extension look like up here? I'm sure you'd say I'm crazy if I said anything other than a straight horizontal line. After all, we are looking for the most natural curve, and I think we'd all agree that any curve that sweeps up and down through a bunch of horizontal points is not the most natural curve. So, a straight line it is. The more symbolic way of saying that our curve is a horizontal line is to just replace little n with x in our approximation, signifying that it holds for real numbers instead of just integers. And now we've done it. We've found our interval, because we can choose the space between any 2 points, and that'll be the interval that we can build the whole function from. Now, I don't know about you, but I think that this process is super cool. We want to find some harmonic number, but we don't know exactly what value it should have. So, we go up to a huge number, capital N, and now there's only one reasonable choice for the corresponding number. And now finally, we can recursively step all the way back. And eventually, we arrive back where we started, locked into one specific value. Alright, now it's time to put everything together. We'll start with our almost equality for large n, and we'll rearrange the terms a bit to say that their difference is pretty much 0. Now, the more precise way to explain what's happening is with limits. Since the difference gets smaller and smaller as n gets larger and larger, the limit as n goes to infinity of this difference is precisely equal to 0. Now, for the h of n, we can just plug in the original definition of the harmonic numbers. For the h of n plus x, we can reposition the n and the x, and now this is just a case of our super recursive formula, so let's plug that in. Now since the h of x doesn't depend on n, it can come outside the limit, and we can subtract the limit out to get h of x by itself. And now we rearrange terms to make it a bit nicer, and since both of these sums go from 1 to n, we can combine them into one single sum. And just as the final touch, we can write the limit with a nice shorthand by just putting an infinity in the top of the sum. And this is it. This is the extension of the harmonic numbers. Alright, now that we have our solution, let's graph it. As far as graphs go, I'd say this is definitely one of the more interesting. It's got an expectedly smooth curve for positive numbers, but there's a vertical asymptote at every single negative integer. I think there's something kind of exciting about complexity unexpectedly emerging from simple questions. And this is a complexity that other extensions of sums don't share. Take, for example, the sum of natural numbers that I mentioned at the beginning of the video. That's just a parabola. And the sum of exponentials turns out to just be another exponential. But take reciprocals, and suddenly things get way more complex. So why do we care about this particular function? Well, if mere curiosity wasn't enough, the method we used, that is, going out to the absolute extreme case where the function's better behaved and using our newfound knowledge to work our way back, is a nice mathematical trick to have up your sleeve. I know I've used it to solve other problems, and you never know when it might come in handy. But in addition to that, it turns out that our function has some surprisingly far-reaching applications. Our solution is actually a shifted copy of a special function called the digamma function. I wouldn't be too surprised if you haven't heard of this function before, but it has close relationships to other functions, such as the gamma function, the trigonometric functions, and the ever-famous Riemann zeta function. But those will all be topics for future videos. So until then, thanks for watching.